it takes a longer time to converge to the value function. So the best way to figure this out is to actually simulate this, like a little piece of code that simulates these sort of episodes and see how many episodes it took for it to actually converge to the true value function of the policy, and it will take longer. So that's basically the direct estimation. So this is the problems with it. And again, this is what it's saying, that, for example, minus 10, this state is minus 10, this says, currently says plus 8, and to get to this guy, both of them have to go through 4. So how can this be minus 10 and this be plus 8? There is a local inconsistency in the value functions. Bellman equation makes sure that the local inconsistencies are all removed. Okay. However, if you want to use the Bellman equation, you need the transitions and the rewards. So that's our first idea, the passive model-based reasoning, which basically, I say the same exact example. I have the same exact example. Okay, where I'm again following the exact policy there. Okay, and I look at the episode, and then based on the episode, I'm not computing the value function, I'm computing the transition function. So I just want to see how many times was I in 3-3. I'm in 3-3 here, I'm in 3-3 here. How many of those times did I do right? Both times it looks like I've done a 3-3 right here, 3-3 right here, 3-3 right here. Okay, when I did 3-3 right, how many of those times the next state was 4-3? Here it was. Here it was 3-2, it's a different state. Here it is 3-2, it's a different state. So, when I did right from 3-3, I got to 4-3, 1 out of 8 different times that I've done it. You just see what I said? Does it look very complicated? This is actually taking ratios. So, 3-3 right, 4-3 is 1 over 3. Now, is this correct? Well, it is correct if you do it many times. And, then basically asymptotically it will be the correct probability. So, I am computing the probability empirically, I am estimating the probability empirically. Right? Yes?
So in the two situations where we were 3-3 and we went right, and we didn't go to 4-3, is that because the probability of going right is not equal to 1?
Yeah, so remember you didn't know this stuff, you just are figuring this out. I mean, there are two pieces here. One is you know as an oracle what the probabilities are, but your algorithm doesn't know this. Your agent doesn't know it. The agent is essentially assumes what it sees. And what it is seeing is when it is doing right from 3-3, sometimes it's going to 4-3, sometimes not. And in particular, after 3 times it did right in 3-3, it went to 4-3 only once. So the probability of 3-3 right 4-3 is 1 over 3. What is the transition function? It is numbers T, S, A, S dash. I'm telling you how to compute T, S, A, S dash. It's extremely simple for your computer to do. It's kind of painfully repetitive for you to do it, but it's very simple for a computer. Now, if I remember, if I got these things, and one other thing is, as I was doing it for each state, I have figured out the reward. I experienced the reward. And I know the rewards are non-stationary. Again, that's another definition. That's another of the assumptions we have made. If the rewards are non-stationary, I know that if I ever go to R33 and do right to go to 4-3, I will get a reward minus 2. So the rewards at RSAS dash as well as PSAS dash are computed for now. If I do that, then how do I compute the value function? I use the Bellman update. Okay? I use the Bellman equations. So remember the definition of default, you just use the definition of default to compute the values of the state in terms of the values of its neighboring states. In particular, you will get a bunch of linear equations, you solve them, you get all their values at the same. No value iteration, just set of linear equations. That's passive reinforcement learning, passive model-based reinforcement learning. And the last thing that I'm going to mention to you is active model-based reinforcement. Active model-based reinforcement learning, notice that what you're computing is the T and R values, right? You get that? You get the T and R values. Imagine I did have a policy. Imagine I just randomly selected an action at each point. Will any of our computations change? When I was looking at this, did I really care about the fact that in 1-1 I'm supposed to do up according to this policy? I wasn't even looking at this policy when I was doing this stuff. If I'm actually doing active learning, then I just pick up my action. In the beginning, I don't know what actions to do, so minimum, and a simple idea would be that in the beginning, I do some random actions. At every stage, I do a random action. And then I will experience the world. Do something and experience the world. When you experience the world, you can take your experiences and convert them into a transition function. Notice that the transition of an action right, taking you from 3-3 to 4-3, doesn't depend on which policy you were using when you decided to do right. Do you understand what I'm saying? Whether you had made a great plan and according to that plan you're supposed to turn right at this intersection, or you had no plan and just randomly turned right at this intersection, what happens after you do turn right has nothing to do with whether you thought about the full plan you put on. The reward you get is just the property of the environment. So if you do these random actions, then essentially you'll get the transition probabilities. And in fact, what you could do is you behave in the world randomly for a whole bunch of time until cows come home. Asymptotically long amount of time. And then convert it into transition values. Transition probabilities. Now, instead of doing V pi calculation, I do the V star calculation. They're just two different calculations. If I give you R, T, and pi, you can compute just the value of that pi. If I give you R and T alone, you can just directly compute the value optimal policy. In fact, one of the interesting things you could have done is even in the passive case, even though you have this policy that you've been following, and this is what you got these episodes from, once you got your transition probabilities, you don't owe it to anybody to only compute V pi. You could actually have computed V star. And if you do that, what would happen is, if there are any local inconsistencies in the policy you are following, you will figure that out. It would be a policy iteration step. Okay, so active model-based learning is very simple. You just do randomly going around. The problem is, when we come back, we'll get to this exploration-exploitation trade-off, because if you keep on doing things randomly, it will take a long time to learn about the world. You will learn. If you randomly explore, you will learn. Everything that is there to be learned about the world. But it will take a long time. You might die. So the temptation you have is, after a bit of random exploration, you compute the optimal policy with respect to those transition values. At this point, you have an optimal policy. Would you just keep doing that, or still continue to do random walk? The answer is, if you just stick at any point of time to the optimum at that point, you're being greedy. You are exploiting your incomplete knowledge. If you're always random, you are never greedy, you are never exploiting, you're always exploring. Exploration exploitation can be had by taking the optimal policy with respect to this incomplete model you have, and with any time and next time when you have to do an action, with probability P, do what the policy, optimal policy says. With probability 1 minus P, toss a coin and do something random. Now you understand, people give you this kind of advice. Once in a while do something crazy. Who are these people who are giving you this advice? They have taken reinforcement learning class and have realized that you cannot just exploit because the world is too big. There are states that you haven't seen. So every once in a while do something crazy. That's the lesson today. That's the exploitation trade-off. We'll start from here.